Welcome to section 3.2 for logarithmic functions. In this section, we're going to look at graphs, and we're going to look at some applications. And then we're also going to introduce the natural log and the common logs. As we discussed in the previous section, the domain of a logarithmic function, so the numbers we are allowed to plug into the basic logarithmic parent function, is any numbers that are greater than 0. And the outcomes of my logarithmic functions are really all the values negative infinity to positive infinity. With logarithms, of course, we cannot put in 0, and we also cannot put in negative numbers, because what we were looking at, we are assuming that a, the base, is greater than 0. Therefore, if my base is greater than 0, we're never going to have a negative outcome when we raise that to a power. So as we look at graphing logarithmic functions, it's helpful for us to know what the general look of them is, and to kind of get an approach. One of the things that I personally find helpful is to start with larger x values and then go to smaller values. And you can see over here that these are the values I've chosen. Now, I chose these very specifically because 3 is my base. If 3 is my base, then what I'm inputting here, I want to be an outcome of raising that base to a power. So, for example, let's look at my first input here, which is x equal to 9. If I were to find the y equal to the log base 3 of 9, what I'm looking for is what power of 3 would result in a 9. In other words, 3 to what power gives me 9 as an outcome? And the answer there is 2. So the y outcome for this is 2. If we replace the net with or if we replace the 9 with our next number here, which you can see I jumped to a 3 because we want to know what 3 to what power will give me 3. This, of course, is 1. It is one of our properties of logarithms. When the base matches that, we get 1 as a result, because basically we're just looking at whatever the power is, and there's kind of an unspoken 1 there. And so the input of 3, so we take the log base 3 of 3, we get 1 as an outcome. The next number I put in is 1, and 1 is something you can use for every number, or any logarithm. The outcome of 1 there means 3 to what power gives me 1, and any base raised to the 0 power results in a 1. And so my outcome here is 0. All right, and then we get into the fractions, and this is where it's weird. Basically, I can use the inputs that I have here where the denominators are, again, powers of 3. And so the outcomes here will just be the same as the outcomes I had over here, except they'd be negative. In other words, for the log base 3 of a third, 3 to the 1 negative 1 results in 1/3. Let me go ahead and write that down over here. It'll help you to see it visually. Log base 3 of 1/3. So we're ostensibly thinking 3 to what power results in 1/3, and the idea there is 3 to the negative 1. So my log of log base 3 of 1/3 is negative 1. This will be negative 2, and of course this will be negative 3. So it's the same outputs that we had before, except they're negative once we start getting into the fractions. In fact, whenever you're taking the log of some sort of fraction, the log outcome should be negative. All right. So 9, 2 is one of my points. 3, 1 is one of my ordered pairs. 1, 0, 1/3, -1, 1/9, -2, and 1/27, -3. So as we plot these out, 9 gives me 2, 3 gave me 1, and 1 gave me 0. And this part is a little hard to see, but if I go a third, I go down 1. If I go to the right 1/9, I go down 2, 1/27. So as soon as I get really close to that x-axis or the y-axis really quickly. And we can see, like, domain-wise, that we're only plugging in positive values for x. And the outcomes will continue to rise, but they rise at a very slow rate. My next point here, if I have, if my input is 27, if I was going backwards there, so I have to go out 27, I would go up one more unit. So, and then the next one after that would be the next multiple of that, which I believe is in the 70s, which will take you up to 4. Anyway, you get the idea that this becomes, I think it's 81, sorry, not 70s, that you have to go out further and further and further for it to rise one more. But if it keeps going in that direction, the pattern tells us eventually we could get every range value possible for y. Let's take a look at another one. Here I'm doing a log base 2 instead of a log base 3. Okay, so the first input of x for my log function is 8. And again, 8 I chose because it is a multiple of 2. And let's see, so that would be the log base 2 of x, which is 8. So in other words, 2 to what power gives me 8? And that would be 2 to the third power. And then for 4, we think 2 to what power gives me 4? Well, 2 squared. 2 to the 1 gives me 2. 2 to the 0 gives me 1. And then we have -1 and -2. All right, so plotting these out, we see a very similar thing to what I had before, but it's not quite, well, it's rising quicker. You'll notice it didn't, on the previous one, I had to go out to 9, and it only rose 2 units. Here at 8, I'm rising 3, 4, I've risen 2, 2, I've risen 1, and 1, I'm at 0, and then 1/2, -1, 1/4. All right, so the only differences here is that our 2 is actually rising a little bit quicker than the other one when it was a log base 3. Another way to sketch the graph, and is really kind of, in a way, what we were thinking, at least when we were evaluating our log functions, is in our minds we were taking the base of the logarithmic, log base 3, and we were thinking, okay, for this x, 3 to what power resulted in that x? Right? So we were looking at the base and we're thinking, okay, with the 9 here, 3 to what power gives me 9? And we knew the answer was 2. So at any rate, we're kind of doing that mentally, but the graph also, because these are inverse functions, if we fold it across the line y equal to x, which is that 45-degree line there passing through the origin, gives us a matching equation. And so, with the inverse functions, basically we switch the x and the y. So instead of 1, 3, we would graph 3, 1. Instead of 0, 1, we graph 1, 0, so on and so forth. Not quite as practical to do that, but it is another method that we could use. Okay, so keeping in mind also that they are inverse functions, we can see with my logarithm versus the exponential function that my domain, negative infinity to positive infinity, is the range of the log function, and the range of my exponential function, the outcome is never negative. Here, the input is never negative. It's always greater than 0. Excuse me. And the y-intercept is 1 here. Here, the x-intercept is 1. There is no intercept with the x-intercept with the exponential function, because we're always above the x-axis. We're always positive, right? 0 to infinity. And for the logarithmic function, we never cross the y-axis. Here, the x-axis is the horizontal asymptote, and with the log, the y-axis is the vertical asymptote. So definite relationships there, but that's where we see that sort of inverse relationship. Also, the exponential function is 1 to 1, meaning every x gives me 1y, and every y has 1x. So at any rate, if a to the u is equal to a to the v, that's only going to be true if u is equal to b. The logarithmic function also is 1 to 1, and the log base a of u is equal to the log base a of v, if and only if u is equal to v. So it's also true in the other direction. Whenever we have that if and only if, it just means it's true in the other direction as well. If u equals v, then log base a of u is equal to log base a of v, and it goes both ways. The function is increasing if a is greater than 1, and it's decreasing if it's a fraction. We saw we have exponential decay if we have a fractional base, and we have exponential growth if a, the base, is more than 1. And that's actually the same is true over here. If a is greater than 1, then we have an increasing function, and it's decreasing if a is a fractional value between 0 and 1. We can look at some common patterns that we saw actually in all of the graphs that we graphed currently that kind of translate, and it all depends on your base of a. But you'll notice that 1, 0 was a point that we had, if it's a parent function, right? We haven't added or subtracted it in any way. 1, 0 is a point, whether a is greater than 1, or if a is a fractional value between 0 and 1. And remembering that x is my input, when I actually had a as my input, so my input is matching the base, this gives me that log base a of a, and log base a of a is 1. A to what power gives me a? 1. So the only difference here, and you can see actually a fractional logarithm with a fractional base of a, takes on a very different look. Keep in mind here that a was larger than 1, so my a resulting in 1 happened after my x-intercept. But in a fractional situation, that a, always giving me 1, would happen before I reached 1, 0, because a is a value between 0 and 1. And then I get at negative 1 as my output. That happens when I have 1 over the a value. With the base 3, it was 1/3. So 1/3 gave me negative 1. With a fractional, when we think of 1 over a fraction, so let's say my a value was 1/2. Let's just say that was my base, right? So I have log base 1/2. And my input is 1 half, or I'm sorry, 1 over that. So my x input was 1 over 1 half. So in other words, 1 divided by 1 half is 1 divided by 1 half is 1 times 2 over 1, so 2. So at log of base 1 half of 2, so the 1 over that, so that's my input, 1 over 1 half, so my input is 2. The result, the way I get it, is only 1 half to the negative 1 is going to result in 2, so the output of the logarithm is negative 1. That happened over here, like when my base was 3, at 1/3, for my input I got negative 1. Here I would be out further past 1 for that to happen. At any rate, these are the two sort of parent graphs you can have and kind of work with, but those values there, 1 over a, giving you negative 1, 1, 0, and then a1, are reliable points that we can use when visualizing and thinking of the parent graph. As far as the transformations of my graphs, this is a very helpful chart we can use, but it's really following the same patterns that we've seen. With my parent graph here, log base a of x, if we add c, it moves all my y's up by c units. If we subtract c, it moves all my y values down c units. Horizontally, if I subtract, it actually moves the x's to the right one, c units. If I add c, so I'm adding to x before I take the log, it actually moves the x values to the left. If we have the negative, then it takes, it reflects it basically across the x-axis. And if it's negative and it's a negative x, then it reflects it across the y-axis. So that negative x, and whenever we see a minus in front of the x there, we're going to be reflecting it across the y-axis. Also, if we have a negative, we've negated it as well. Okay, and then we have the stretching or compressing, and I wouldn't worry so much with that, this last one there. Think of only in the vertical terms of stretching and compression. All right, so let's play around with these translations with some graphs here, and I've graphed out the parent function here. All of these have the same parent function with the base 3, and so I also wrote out the points there for those, and simply because we can just focus now on manipulating the points that I have. So if we add 2, of course, we know that that shifts it horizontally 2 units. So here, with some of my points, this point here is at 1/3 negative 1. So if I shift that up 2 units, I'm at 1/3. Sorry, 1/3 1. Here I'm at 1, 0. Shifting that up 2 units. Here we're at 3, 1. So this would be at 3, 3. And here I'm at 9, 2. And move me up to 9, 4. I haven't shifted horizontally at all, but really I've just moved up all my y values 2 units from where they were previously. And this, of course, is going to go down to infinity as well. So it kind of looks like, it's hard to see the shifting with those really, really small x values, but they are shifting nonetheless. Shifting this to the right one, my new vertical asymptote will be here. And so this would move to the right one. This would move, let's see, this is at 1, 0, to the right one. So instead of 3 giving me 1, now 4 is going to give me 1. And then instead of 9 giving me 2, now 10 is going to give me 2. All right, so that vertical asymptote is there, and there is my transformation. Again, a little harder to see it because we're really close in here with those x's and the y's. It hasn't, in other words, by the time I get to 10, blue really isn't much higher than the red one is. Remember that I had to go up 1 unit. I had to go all the way from 3 to 9, and then the next bump upward is going to be 27. So it's hard to see here, but we can see kind of clearly here that we've moved to the right one at those lower numbers. All right, and here's a reflection where we're going to reflect it across the x-axis. So the one point where they will share, there's at 1, 0, and then we'll be at 1/3 will give me +1 instead of -1, and 1/9, 2, 1/27 will give me +3, and then at 3 we'll be at -1, and then at 9 we'd be at -2. And here we go. So there is that function. Again, we're using the negative, the reflection of it. That's the only thing that's different between this function and its parent function. On this one, we're multiplying by 2. So whatever y outcome we had, it's getting multiplied by 2. Now, 0, oops. I just lost my graph there, so I'm going to redraw it. Forgot I had it on eraser. And so by the time I get to the y outcome of 1, I would be at a y outcome of 2, 1 times 2. At a y outcome of 0, 0 times 2 is still 0. And then for 9, we would be at 4. Oops, I think I went too high there. At 9, we'd be at 4 instead of y being at 2. So we can see that I'm rising a lot quicker than I was before because we're doubling the y output each time. Looking back for our fractional ones, the same is true, but it's going to happen in a negative direction. For the original 1/3 gave me 1. 3 to the -1 is 1/3. So 1/3 of the logarithm, my input of the logarithm, results in -1, -2, and -3. All these are going to be doubled. So that would be -2, -4, -6. So at 1/3 then, x equal to 1/3, we would go down 2 units. And then at x equal to 1/9, we would go down 4 units. And then 1/27 would be at -6. So it's really hard to see any differences there. There really aren't many. But we do have that crossing. These do share that point there. And it's going down a lot quicker with each x value. Now, some of you may have played around with your calculators a little bit because there are logarithms listed on your calculators. If you use the log button, it says log of x, you've actually been using a common logarithm. The common logarithm has a base 10. And in fact, generally, if you see log x, it's assumed that the base will be 10. And so they don't even write it. So the log that you see on your calculator is actually log base 10. That's why if you try to plug some of these using your calculator, you're not getting the same results. That's because you're operating with the base 10. And most of what we've been, at least our examples and such, have been with log base 2 and 3. So if we have a log base 10, looking at the regular logarithm properties that we used before, they still apply, obviously. Log of 10 should be 1, right? Because this is 10. It's implied that there's a 10 there if it's not written. 10 to what power results into 10? Well, 10 to the 1 power. And log of 1 is 10 to what power gives me 1? Well, again, anything to the 0 power results in a 1. And this is log with the same base of the same number raised to the power. We can see this would be 10 to the 1 up here. So if there's another power there, that's going to be the result of my logarithm, just like 1 was the result here. And if we have an exponential statement with the log in the exponent, again, the base here and the base of the log match up, we also get x. And we know that x will be something positive. The other type of logarithm that you'll see on your calculator is the natural logarithm. And that's and it's actually has a different look to it. It's not log. We put ln of x rather than log, natural log. And so what that is a log base e. It's implied with ln of x that is a log with a base e. That e is that Euler number, that naturally occurring number. This is why we call it the natural logarithm. And in fact, ln of x and e of, well, x on your calculator at least, is they're opposites. But again, it's the outcome of my natural log is the exponent with a base e, same base that we have over here. So, same things here. Natural log base e of e is 1. Natural log of e resulting in 1 means e has to be 0. The power of e has to be 0. And we see all of these similar things here. X and e to the natural log of x is x as well. In evaluating some of these natural logarithms, maybe visually it might be easier for you if you see them in terms, as you're getting used to this, you're not really going to use your calculators for any of these that we're doing in these first two sections, a couple sections at least. But this would be the log. The natural log is log base e of e to the 4th. And we know that when I have the same base of that, whatever power we have, that's actually the result or the answer of my logarithm. For the next one, again, if we write this as log base e, we're taking 1 over e to the 2.5, kind of an odd thing. And so we think, okay, well, does, we know over here if the base and what we're taking it of match up, then we look at the power. But here, the base is actually in a denominator. But I can rewrite this. Remember that when we move things to a denominator, it's because the exponent is negative. In other words, e to the minus 2.5 is equal to 1 over e to the positive 2.5. Once we've moved it, it becomes positive, like this particular one is. So another way I could look at this is log base e of e to the negative 2.5, and then this follows in the same problem I had previously. We know that 4 is the outcome there. And looking at this one, log base e of 3, in other words, e to what power results in 3. If you remember, e is a number. It's 2.71 something, something, something that repeats forever without a pattern. So that 2.7 something, I don't really know what the power would have to be to result in 3. So here we would need to use our calculators. We would go to the ln button on our calculators and do the ln of 3. And what we see is approximate. Since we're going to have to round it, I'm going to use the approximate symbols. 1.0986123 is about as far as I want to go there. That's the approximate result. So e to this power, which is a decimal, crazy as it is, would result in an outcome of 3. Okay, so let's work a couple of application problems here. And we're going to see how long it would take me to double my money if we were earning 6.5% and was compounded continuously. Or that continuous compounding of money was an E formula. Specifically, the amount in the account is equal to my principal multiplied by E to raised to the rate multiplied by the time in years. Now, we're looking for our money to double, and we want to know how long it's going to take. So really, eventually, we're trying to solve for the exponent here. This is where logs can be helpful to us. So first of all, P is my original amount, right? And so if I want the amount in my account to be double that, it's going to be double my principal. So I'm going to go ahead and put that in for A. I want the amount to be twice what the principal was over here. And so this will work for any amount, no matter what the principal. It's still going to tell us how long it would take. And so, okay, so we have 2P equals PE-RT. I'll write it again. And what I want to do is to get that base E with the powers by itself. So I'm going to move the P to the other side. And that does a couple of things for me. Since I replaced A with my desired outcome, which was double P, 2 times P, and I dividing by P, that P actually goes away, which is kind of nice, because again, we want to solve for one variable. The other number I do know as well is the rate. And so I'm going to replace that. Move this over here. So 2 equals E. I'm going to put the rate in decimal. So 6.5% would be 0.065. And multiplied by T. Remember that E is not a variable, even though it's a letter. It's representing, kind of like pi does, a very specific number. And that's just easy to, that's something you want to keep in mind because remember, T is the only variable we have left, and we like that because that's the one we're trying to solve for. So I was able to get rid of A and P because there was a relationship there, and then I divided P out. I knew what the rate of interest was, and that just leaves me with T to find. Since T is in the exponent there, I'm going to take the natural log of both sides. All right, so I took the log of this side, and I took the natural log of the other side. And remember, ln of E is log base E of E. And so the E base with the base to the power being the same, that basically gives me the exponent, which is 0.065t. And over here I have the ln of 2. That is something that can be done on a calculator. And in fact, if I want to solve for t now, I've taken it out of the exponent. And so I have t equal to ln of 2 over 0.065. And that's something I want to put into my calculator. And if we do that, we see that t is equal to about 10.66. So it's about, if we rounded it, 11 years or so that it would take me to double my investment at a rate of 6.5%. It would actually happen within, if it's compounded continuously, 10 and almost 2/3 of the year, so somewhere around, I guess, October or so. And that's how long it would take me to double my money at that particular rate of interest. At the second question, it says, what is the rate of return? At what rate of return, compounded continuously, would your money double in 5 years? So let's tackle that. So, at what rate of return, compounded continuously, would our money double in 5 years. So now we have the time that we want to invest the money. But we want to know, all right, well, what's the rate of return I would need to get? Because 10, 11 years, that's a long way to wait. So at any rate, twice the principal, 2p is my amount, equals p multiplied by e to the RT. But my time now I know, so I'm going to go ahead and replace that. Okay, so R is what I want to solve for, and we know T is 5. So 5 times R. All right, I can get rid of P just like I had before, dividing on both sides. That gives me 2 equals E to the 5R. And taking the ln of both sides, that's ln, so log base E of E. That just leaves me with the exponent there, 5R, ln of 2, divide both sides by 5. I get my R equal to, and this is the amount of the interest that I would need to double it in 5 years, 0.1386. So 13.86% is the percentage return I would need to give, or I would need to get in order to double my money. So we can see that how the logarithms are something we can use. Whatever your base is, that's the log you want to take. If this was P2RT, and, if that's what I've left over, I got rid of P, then I would want to take the log base 2 of 2, which would get the R and T out of the exponent, and then I could solve for either R or T depending on what the problem is asking me to do. This is one of the big things that is helpful for us with logs. It helps us to evaluate values that are in variables that are in exponents, that are in powers. And it used to be that we had to have these big long tables that we had to look up, but luckily with technology, solving these is pretty simple math for us.